So now we are ready to start our meshing process. I work in Linux. If I want to use openFOAM, and first step what we need is to go to our folder. I already created a folder run mesh Mercedes-Benz 126, and here I put my preform template files like block mesh, cfMesh, meshdict, and so on. And and here I have also two folders for run meshing in cfMesh and run meshing in Snappy. I would like to go through them folder and explain what is necessary to have in each of it. So by running of cfMesh, we need to have constant folder with tri-surface and all our boundaries exported as STLs. I have also created a copy with origin because we need to edit these files to one STL combined file. The next what we need is system folder, where we have control dict, mesh dict, and surface feature extract dict. And in main folder we have cfMesh and openFOAM run. You can see here the comments what we need to for starting cfMesh. Here the same situation by Snappy. We have constant tri-surface folder with STL files. Then we have system folder with block mesh dict, decomposer part dict, mesh quality, snappy mesh quality dict, snappyHexMesh dict, and surface feature extract dict. For any reason, I don't know, Snappy meshing process need also control dict, FV schemes, FV solution. I think we can let them. We can stay them in the folder, and now I go quickly through system dictionaries. For example, we have to edit the decomposer part dict because I have a big machine with 16 cores. Here we have to write 16 cores instead of 4, as it was previously defined. When we go to decomposer snappyHexMesh dict, here we define, here you can see castellated mesh, snap, add layers, refinement objects, and here we have to redefine the max global cells. We have to increase it up to 50 millions and divide them to up to 16 processors, and we have 3,125,000 cells for each processors. So now we can scroll through it. Here we have wall slip, where we defined our 5 layers, and here we have the mesh quality control. Okay, it's Snappy editing is done. Now we can open the terminal, activate openFOAM, delete all what we do not need, and you can find here the commands: remove FR constant polymesh, remove constant tri-surface eMesh, and so on. And then we are ready to start Snappy and we begin with block mesh. First command runs well. I have also log file which we will see next. After block mesh, we have to run surface feature extract dictionary. It's also run well. And in the next step, we decompose and run snappy in parallel. After that, we reconstruct ParaMesh and check and make the check mesh. Let us begin. I will look until the snappy execution is running, and after that I interrupt the recording and open it or start another recording first when the meshing process in snappy is ready. Now the calculation is done, meshing process is at the end, and now I have to check some things. First of it, I will check log files, and the second check will be the check of mesh quality. So I open my folder and go through the log files. Block mesh we have already seen. We can start with snappy. Snappy begins with defining of levels and defining the number of cells on each level. After it cut, now we go forward. Here we see, and here begins the process of snapping. Here the settings, parameters for mesh quality dict. These settings are default. You can use them and write each of it separately, or you can use only mesh quality dict. So let us go through snappy further. This is the snapping process, and at the end we will find the add layer process. The process for layer creation begins here. Number of layers, and it begins here. So that is how snappy run. Then we have to look on snappy log. Yeah, and the last one is check mesh. So for check mesh, I can say that we in total have 11 million of cells. Now we have here 3 phase stats with low quality, cells with small determinant, 11 cells, and here we have 3 mesh checks failed. Now we can go to ParaView and see each of them, or see the cells with low determinant and with low phase state quality. Let us begin. Go to media, RAID, Mercedes-Benz steady, run snappy, start snappy form to form, and of course I want to see the internal mesh. So this is edges. Then I add also post-processing, low quality dead faces, I have to define them as a point and give the point size 20. So let me see what we can also. Undetermined cells, yes, it's also necessary to know. And the last settings, failed mesh setting is concave cells. It's not necessary because this setting is not critical for meshing. So let me define the undetermined cells as well as low quality phase stats as points, and give them the size of 20. So now I shut them down, and at first we will start. We want to see the cutting plane. So here we see our refinement objects. Now in this section we see only two of them. We see bounding box number 1 with a smaller dimension but a higher refinement level, and the second one is bounding box, refinement box 2 with a lower refinement level as previous one. So here we can also see the layers which were created along walls slip. That means both side walls and upper wall. So now I want to see the refinement objects in Z coordinate. So I don't want to show the plane, and I press apply. So here we can see all of refinement objects were created. For example, you can see here spheres. We have 4 spheres defined with refinement level, I think it was 4. Then we have 4 hollow cones. This is the one, this is the next one, this is the next one, this is the next one, the 4th one. So we can see also the normal cones, and at the end we can also see cylinder refinements. So now I turn on the faces with low TED quality, and you can see where the faces are to find. So you can, from now you can understand more about why it comes to this face stats quality problem, and approximately you can create a solution for this problem. And now you can take some undetermined cells. 11 of them are on their wheel, and that's all of them. So I can also, let me show the same on the body of car. For that I have to select Mercedes-Benz, and let me also select the road for better understanding. Here you can see where the low quality cells are positioned. So the next step, what I want to do is I want to run the same case, but with the best quality settings for mesh quality dict, and let me see after it of if we find some undetermined cells or not, or if we find some other mesh failures or not. Here's the mesh quality check, and keep it in mind, we have failed 3 mesh checks: error in phase states, small determinant, and some failures on some errors on concave cells. Now I have to remove. Here I remove all what I do not need here for starting. Here we are, and now I start snappy and openFOAM run directly with block mesh until check mesh. Now it's running, and I interrupt the recording, and after after the mesh creation is done, I start a new session. So now is the meshing process over, and we have to look on check mesh. You can see that we do not have any problem with phase states. Only 4 cells with small determinant, and in comparison to previous meshing with mesh quality settings as default, we have here a huge improvement. And now we can also look at the geometry. This geometry is the previous one with problem with low phase states and with problem on determined cells. And now I upload the form with good quality, and show you also the differences. For that case we need only the road and Mercedes-Benz walls. We don't need to investigate another time our refinement objects. They are exactly the same, they should be exactly the same. So good quality, so face with edges, solid color. So now you can see that how this geometry looks like. I also upload the four undetermined cells and give them size of 20. You see here we can find these 2 or 4 undetermined cells. Here you can see also in the back on the rod also bad determined cells. Now I'm very happy that my advanced mesh quality settings cause lower mesh quality problems. What I can also mention here, each time when you want to create a mesh with good quality, you have to choose between good quality or best quality and between best geometry reproduction, so that every edge in Snappy is exactly the same as the edge of STL file. You can see that some of edges are not exactly the same as it was on STL file. You can see, for example, here on this place at motor here, and let me show the default settings. So the previous one, it is not much differences what we can see, but let me run the last simulation in Snappy, or last simulation according where we can define our quality. And now I will try to create the geometry, the mesh with best geometry reproduction. So we have a lower quality, but instead of it we have a best geometry reproduction, so that the cells like this will not be created. For that I change my snappyHexMesh dict settings on mesh quality control and run the another meshing process. After the meshing is done, I start a new recording session. So now I have to delete all unnecessary files. This here, and I need to run Snappy again, starting with block mesh dict, surface feature extract dict, and so on. Here we see that the mesh process is over, and we have here 3 failed mesh checks. We have some problems at face stats, and some problems with small determinant cells with a small determinant. So now I open the last Snappy trial where we plays with mesh quality settings. In this trial we wanted to create a mesh with the best geometry reproduction. So here I see that the geometry corresponds to the STL file as much as possible. Let me click it, let me turn it on, and you see, if we leave only the STL file, you see that each edge is exactly the edge what we created in design modeler. And if we are looking for good quality but not a good geometry reproduction. We see some cells which are not corresponding to the STL file. And if we look on the mesh with the best geometry reproduction settings, we see that they are as close as it possible to STL file. So that was the last thing what I wanted to do in order to compare the quality or geometry reproductivity. The next case we will start cfMesh dict. To start the cfMesh, we have to change the folder, and I will press call directory, and we go to cfMesh. Here we will do the same operation and remove everything what we don't need. And especially for cfMesh creation, we need to do following things. So steady again, that's it. We go to cfMesh and open. Here we can close snappy and snappy run and open the cfMesh and openFOAM run. And now we have to do the following things. I have to lay STL combine, rename the files and delete text py script, and run the command Python and run this command. So let me go to constant trisurface and open a terminal. So I activate openFOAM, then I have to copy this file into this directory. Then I have to run the command written below, Python that's it. This command create the STL combined file. That means it takes inlet points and vertices, edges, and so on. The same, it puts outlets and put them together, and we can see the result here. Solid out, we have here STL combined, solid outlet, then solid inlet, solid walls, and so on. The number will be not here defined. The number will be defined after executing of the following command: surface feature edges STL combine STL to FMS combine FMS. We have to create from STL combine STL the FMS combine FMS file, and let me do it by executing of this command. Now it's done, and we see FMS combined file. This is a necessary file for cfMesh dict. Here we have a mount, 6 separate files or boundaries: outlet, inlet, walls. So let me close it, and now we are able to start cfMesh, because for starting we need to have fms combine fms file, and then I close this terminal and run the command with delete of all another time, and here we will run the cfMesh with we will run cfMesh with improved mesh quality. So that means we starting with surface feature extract, then we make Cartesian mesh. This is the command for creating of hexaeder dominant or hexaeder cells in the mesh. We have also the possibility to create TET mesh, tetrahedral mesh or polymesh, but now we will compare the snappy with cfMesh and create also for that the Cartesian mesh. So then we improve mesh quality and make the check mesh. So let me start. What is good on cfMesh is that cfMesh run with maximal power of your PC, so it takes as much as possible processors, and what is also good, you don't need to define any mesh quality settings. It will be done automatically, but because of it sometimes we have problem with mesh quality. Let us run cfMesh dict and the cfMesh dict process, and then after it ready we will show the result and compare it with snappy. cfMesh is done, and let us have a look on checkMesh file. So we have here error, cannot find the file FV schemes. Please excuse me, because I say that we don't need FV schemes. Okay, I go to system by snappy and copy it to cfMesh. Now we have in system dict FV schemes and FV solutions, so we can start again, run the cfMesh. The meshing process as it is done, but the problem is that we don't have a checkMesh file, and we need it for our discussion and comparison to snappy. So I delete everything what is done and start again surface feature extract dict and cfMesh. So I'm back, meshing is done, cfMesh is ready, and now we can see the checkMesh file. It's also included. At first I want to compare the number of cells between cfMesh and snappy. In snappy we had quite a little bit more than 11 million, and in cfMesh we have 12 million cells. It's for me the number of cells is most the same as in snappy. So we go forward, and I see here 5 failed mesh checks. For example, phase pyramids, error in phase pyramids, max skewness, error in phase stats, and cells with small determinant. So as I mentioned before, the quality of cfMesh is not so good as in Snappy, because in Snappy we have to choose between best quality or best geometry replication. So the goals of cfMesh, they should be considered in comparison with its mesh quality. So we don't need to define the block mesh in cfMesh. We don't need to set mesh quality or layer settings or layer quality settings. We don't need a decompose par dictionary for cfMesh, but the mesh quality is a little bit worse than by Snappy. In some application, the quality goes first. So now we can open the ParaView and consider the Snappy with cfMesh. So I go to cfMesh and open openFOAM file. First I will show you the mesh itself as internal mesh. Here it is. So let's look on section. Here you see the same blocks, refinement regions as in Snappy. I also can show you the section along Z X direction. Sorry, we have to invert it. So now here we see the same situation as in Snappy. In comparison, I can show you. This is comparison. In this comparison, we see that cfMesh is equal to Snappy. In some cases, we need to keep the number of cells as low as it possible. For example, if you have a student version of Ansys Fluent, you have to keep the number of cells under 200,000. And now I want to show you how easy is it to decrease the number of cells in Snappy, and then we start to do the same in cfMesh. Now I want to show you how easy is it to minimize the cells number in Snappy or in cfMesh. For that I have to go to the snappyHexMesh dict and cfMesh dict. First, we reduce the number of cells by commenting out of all refinement objects. Let me do this. the next step. I have to reduce the numbers of cells. In Snappy is it easy to do, and I want to have only the one cells between the levels. The last thing I want to do in snappyHexMesh dict is to reduce the min level on refinement surfaces. I reduce it to 0, and we will look what happens after the meshing. The same process I do in cfMesh. I comment out the refinement objects, and here I have to reduce here I have to reduce the surface mesh refinement level on here on walls rod fine and on walls Mercedes-Benz. I want to save it as well as snappy, and now I have to change the block mesh dict for snappy, and also make a smaller inlet outlet walls slip and walls rod fine boxes. Here you see I prepared a smaller export. Here we can see the inlet outlet walls rod fine and walls slip. These files I have to import into constant tri-surface as well by cfMesh dict as well by snappy. That's done. Now I run the style combine file in cfMesh in order to create a style combined file, and after that to convert it into FMAS file. So let me do that. I activate the openFOAM, then I have to run Python and convert the file extension. So now is everything done, and I close this terminal. So let me start with the snappy, and of course I have to delete all files what were created and started new time. Here we are. Now snappy is running, everything is well. We wait for the end. You see snappy is ready. It was very quickly. So what I want to show you, first I want to let me start the cfMesh. Of course I have to delete everything what was done, and start again cfMesh with improved mesh quality. So let me start until it's, as long as it's run, I can show you the result on Snappy. We have to open here you see the result. We see snappyHexMesh without any refinement objects, and you see all edges have the maximal refinement level, and in the middle of each face we have the minimal refinement level. Now I can show you the problem what we have. Space in a gap is destroyed, and it happens if we have a huge a big cell size between two faces. Now let me look on checkMesh log done by by Snappy. Oh, we have a good result. We have only 2 failed checkMesh, and number of cells is decreased or minimized up to, at first we were we had approximately 11 million cells, and now we have under 1 million cells. Let me show on cfMesh. Is it ready? No, it's not ready. It's running. As long as cfMesh runs, I can also show you the minimized block air volume. Here you see how small it is. I turn it off and wait for cfMesh. Now the cfMesh is also ready. I will have to look on checkMesh file, and you see the cells number is more than in Snappy, 1 million cells over the Snappy. This happens because cfMesh doesn't allow you to reduce number of cells between the levels and keep it always 3. We have 3 cells with the same cell size between 2 refinement levels. That will be better explanation. So now I can show you also the failed mesh checks. We have here 6 failed mesh checks. It's not new for us. I have already said that you cannot change so good the settings for mesh quality in cfMesh. So now we can see on the geometry and look if the same problem with coarse mesh here represented in cfMesh. Have a look at this. So to compare with Snappy, I can show you, switch on the Snappy, and let me go back to cfMesh. I will turn the car in order to see, do we have, let me show you, we do not have the mesh or self-destroyment. Everything is good, so we can let it as it is in cfMesh, and we want to only change something in order to eliminate this problem. We want to change something in snappyHexMesh. So I open the snappyHexMesh dict and then change here the walls mean refinement level and walls road mean refinement level to 1. And let me start snappyHexMesh dict and run. Let me run snappy again. So now snappy is running. I want to change the name of this thing and look again. Now snappy is done. I am interested in check mesh. We have here failed 2 mesh checks. It's a good result. Everything else is good. Now we have instead of 839 we have 842,000 cells. This is also a good result. And let me show you if we have the problem with destroyed cells or not between 2 of the faces in the gap. And now you see we don't have this problem anymore. So what I can say, we decrease the cell size between the car and road, and the problem was solved. Now I want to show you in comparison to cfMesh. Both meshes looks great, and now you can also see here that the number of cells between 2 levels in cfMesh is always 3 cells. You see 1, 2, 3 and 1, 2, 3 and 1, 2, 3 here. That's why we have more cells by cfMesh. And now can you look, we will look on snappyHexMesh dict. You see there are only 1 cells between 2 levels. Now I want to show you how I convert the foam mesh to most important CFD formats for Fluent and CCM+. The commands what we need for that are the following: form to star mesh and form mesh to Fluent. Let me execute them. First I start with snappy, and we will start the command form mesh to Fluent. Here we go, it's running, and in our snappy folder we can find the Fluent interface folder with run snappy .msh extension. Now I will switch to cfMesh and execute the command form to star mesh. I can show you. We can also execute form to inside, form to FireMesh, form to GMV, form to StarMesh, form to surface, and so on. Form to we want in this case form to star mesh. Let me execute the command, and what we find in cfMesh folder, here we can see mesh export. Now it's ready, and these 3 files we have in cfMesh folder. And now it is time to come to conclusion, and I want you to know what we have done and learned in this video. First, we have created the boundaries in Salome and export them as STL files. We prepared the dictionaries, especially the snappy and cfMesh dicts, with my Excel program which generate the scripts. We investigated the behavior of snappyHexMesh tool by running and using different mesh quality control settings. We compared 2 tools, Snappy and cfMesh, and find out that cfMesh is easier to operate, but Snappy has more options for control the mesh quality or layer creation process. We find it out that cfMesh has more cells than Snappy by the same resolution in the same file, and the reason for that was the number of cells between the levels. The number of cells between the levels in cfMesh is always 3. And in the end we converted the FOAM mesh to most important CFD formats for Fluent and Star CCM Plus software. So if you have a question, or you will that I create for you scripts on Snappy or cfMesh, please do not hesitate and contact me. My email is written below. Please excuse me for my English. I have done my best, and in the next time I will do it better. So I will be happy to see you again on my channel or homepage. Have a nice time. Bye bye.